Welcome back to Cyclic. Today we are diving into the KCSE 2024 Chemistry Paper 1. Whether you're feeling confident or a bit nervous, don't worry, I've got you covered. Together we are going to break down everything you need to know, from the key concepts to the tricky questions. By the end of this video, you'll be ready to tackle this paper with full force. So be comfortable, grab a paper and a pen, and let's get started. Question number 1. Name the apparatus that can be used to, part A, measure the volume of solutions more accurately than a measuring cylinder. This, of course, is the burette. Part B, lower a burning piece of magnesium ribbon into a gas jar. This is the deflagrating spoon. Part C, store and keep substances free from moisture. This apparatus is the desiccator. Question number 2. A radioactive isotope decays by either emission of alpha or beta particles. Part A, explain why alpha particles have a higher ionizing power compared to beta particles. Okay. So this question is based on a topic in Form 4. It's actually the last topic of the KCSE syllabus called radioactivity. So first things first, what is radiation? So simply put, this is a process that releases energy in form of particles. Now, in our syllabus, we focus on the following 3 particles: alpha particles, beta particles, and gamma particles. So radiation releases these particles. So it can release one of these particles or a combination of 2 or more. Now, these 3 particles have different energies, and because of this, they tend to have different properties. Now, this particular question draws our attention to the differences that are present in the properties of alpha and beta rays. So the first property is the ionizing power. Now, before I talk about this, let us just remind ourselves of what ionization is. So this is a process that brings about the formation of ions. What are ions? Ions are charged particles. When atoms lose or gain electrons, they form ions. And ions are charged. They can either be positively charged or negatively charged. Sawa? So all of these 3 different rays have the ability to bring about ionization, okay? So they can cause atoms to either lose or gain electrons. Both alpha and beta particles can do this. However, alpha particles have a higher degree of ionization. They bring about ionization more compared to beta particles. Now, the reason for this is, number 1, alpha particles have a positive charge. They actually have a positive charge of 2, okay, plus 2. So what happens is that when they interact with atoms, they can easily pull electrons away from the atoms. Okay, let's imagine we have an alpha particle, and the alpha particle is positively charged. And within an atom, an atom, okay, this is an atom that is going to come into contact with the alpha particle. So within this atom, you're going to have electrons, and electrons are negatively charged. So what do we say about opposites? They attract one another. So the electrons are going to be attracted towards the positively charged alpha particle. So that means that when alpha particles come into contact with atoms, when they interact with atoms, they can cause these atoms to easily lose their electrons. And by doing so, it leads to the formation of ions. Now, the second reason that alpha particles, bring about a higher ionization, compared to beta particles, is that they have a larger mass. So they are heavier than the beta particles, and therefore they move slower. And because of the slow movement, what happens is that they tend to have more time to interact with the atoms as they pass through mediums. So that means if they get to interact with the atoms more, they bring about a higher degree of ionization. They are more likely to cause the atoms to either lose or gain electrons because they tend to interact, more with the atoms because they move slower, right? Now, unlike beta particles, number one, have a negative charge of 1, okay? And they are also lighter. So they move faster and they are overall going to have less contact time with the atoms. So even though beta particles will also bring about ionization, it's not going to be as much as the alpha particles. Okay, I hope that is clear. Part B. Explain how alpha and beta particles can be distinguished in terms of their penetrating power. Now, this is another characteristic. The first characteristic was the ionizing power. Now, we're going to talk about penetration power. So, what is this? Simply put, it's the ability of the radioactive particles to pass through materials, to pass through substances. Now, this is tied to the amount of energy that the particles have and also their speed. Now, when we talked about the alpha particles, we talked about them having a slow speed, right? Because they are heavier and denser, they have more mass. Beta particles, on the other hand, are lighter. So they're going to be faster and they have more energy. So they're going to have a higher penetration power than alpha particles, right? So beta particles can pass through a sheet of paper, but they will be stopped by a sheet of aluminium. Alpha particles, on the other hand, have less energy, they have more mass, they are slower, so they cannot even pass through a sheet of paper, as you can clearly see. By the way, I know that at this point, a lot of you have yet to cover this topic of radioactivity. So if you want a head start, you can just check out my playlist, Radioactivity, where I explain all of this and more in detail. Let's continue to number 3. 3 bottles containing zinc nitrate, aluminium nitrate, or lead-2 nitrate have their labels missing. Okay, so describe a chemical test that can be carried out using aqueous sodium sulfate and aqueous ammonia to label the bottles correctly. Okay, first things first, what do we mean by aqueous sodium sulfate? This is simply sodium sulfate solution. What about aqueous ammonia? This is simply ammonium hydroxide. Now, ammonium hydroxide is used to test for the presence of ZAP, okay? I'm talking about zinc, aluminium, and lead-2 ions. So we use these to identify, the ZAP ions. So how are we going to start with this process? Number 1, we are going to take each of these salts, right? Place a sample in a boiling tube, add distilled water and stir to dissolve, right? Now, once we have that, each of these two, we are going to have 2 samples each. One sample will be for testing using aqueous ammonia. The other sample will be for testing using sodium sulfate. What is our goal? We want that by the end of whatever process we do, we are able to identify conclusively that this contains zinc ions, this contains aluminium ions, and lastly, this has lead-2 ions. So we are going to eliminate one by one until we end up identifying all of them. Now, whenever we use aqueous ammonia to test for the presence of metal cations, what we do is we add a few drops initially and then observe, okay, whether a precipitate has been formed or not. And then we continue adding until in excess. So to the first portion, each add aqueous ammonia dropwise till in excess. So what you'll note that in all of these 3, boiling tubes, you are going to have a white precipitate being formed. Now, the white precipitate will be formed immediately you start adding aqueous ammonia, right? A few drops and you get a white precipitate. Now, the second observation that you should be looking for is when you add excess aqueous ammonia. Now, in the boiling tube containing zinc 2 ions, what you should note is that when you add excess aqueous ammonia, the white precipitate is supposed to dissolve to form a colorless solution. Okay, now zinc ions are the only metal ions out of these three that initially form a white precipitate which then dissolves in excess. So if you have a boiling tube where this is your observation, you can conclusively say that, this was the one that had zinc nitrate solution. So we've managed to eliminate zinc nitrate. So we are left with aluminium nitrate and lead 2 nitrate. We need to identify which is which. So to the second portion of each, what we're going to do is we are going to add 3 drops of sodium sulfate solution. Now, let's look at what we have. In one, we have aluminium nitrate. So aluminium nitrate will react with sodium sulfate to form aluminium sulfate and sodium nitrate. Both of these two salts that are formed are soluble salts. So we are not expecting to see any white precipitate. So if you have a boiling tube and you don't see any white precipitate that is formed, that means that contained aluminium nitrate. So what about the second one, the one that has lead 2 nitrate? What observation will you see? Now, lead 2 nitrate will react with sodium sulfate to form lead sulfate and sodium nitrate. Sodium nitrate, of course, is soluble. All salts of sodium are soluble. What about lead 2 sulfate? This is an insoluble salt. So what should we be expecting? A white precipitate will be formed. So the one that has a white precipitate is the one that contains lead 2 ions. And as such, we have managed to identify each of these 3 salts. Moving on to our next question, consider the following equilibrium reaction for a mixture of gases in a gas series. Okay, so we have nitrogen 4 oxide, okay, at equilibrium with dinitrogen tetraoxide. Okay, so let me explain this. We have 2 compounds, right? Nitrogen 4 oxide and we have dinitrogen tetraoxide. Okay, you're probably thinking where? Let me just break it down for you. Dinitrogen means 2 nitrogen atoms, right? And that is what you have in this compound. Tetraoxide means you have 4 oxygen atoms. And isn't that what we have here? So this compound is called dinitrogen tetraoxide. So how are these 2 compounds related to one another? First things first, dinitrogen tetraoxide is formed when you have 2 nitrogen 4 oxide molecules joining together. You see, 2 of these form one dinitrogen tetraoxide molecule. Now, if we look at our equation, what you'll note is that we have the forward reaction and the backward reaction, right? So I'm going to first talk about the forward reaction. Now, in the forward reaction, this is what is happening. You are going to have 2 molecules of nitrogen 4 oxide combining to form 1 molecule of dinitrogen tetraoxide, right? Now, when it comes to formation of a new compound, okay, this is usually accompanied by the release of heat. You know, heat energy is given off. So what do we call such reactions in chemistry? They are called exothermic reactions. These are simply reactions whereby heat energy is released into the surrounding. So our forward reaction is exothermic because a lot of heat energy is released when dinitrogen tetraoxide is formed. But we also have a second reaction, as we can clearly see from the second arrow. So I'm going to separate this in order to make the information much clearer to us. So this is our backward reaction. So what is happening in this reaction? You are going to have dinitrogen tetraoxide molecule breaking down to form 2 molecules of nitrogen 4 oxide. Essentially, just the reverse of what happened in the forward reaction. Pale tulitengeza, sahi twavunja. So we are breaking down one compound in order to form another. Now, when it comes to breaking down molecules or compounds, this requires an input of energy. And this makes sense, right? If you want to break apart something, you need energy for that. So you're going to need energy in order to break apart the dinitrogen tetraoxide molecule to form the two nitrogen 4 oxide molecules. What do we call such reactions? Endothermic reactions. These are reactions whereby heat energy is absorbed from the surrounding. And this heat energy is what is used to break apart the bonds. Now, I want to talk about the arrows. The arrows tell us a very important message that these two reactions are at equilibrium. So this simply means that the rate at which the forward reaction occurs is equal to the rate of the backward reaction. That means that the forward reaction and the backward reaction occur at the same speed. Okay, so we have these two reactions, an exothermic one and an endothermic one. One releases heat energy, the other absorbs it. But overall, when these two are combined, we still find that the reaction is exothermic. Why? Oh, how does this happen? The reason is because more heat energy is released than what is absorbed. More is released than what is absorbed. So the excess energy is released as heat, making the overall reaction to be exothermic. Part A. Give a reason why the enthalpy change is negative. Exothermic reaction. Now, exothermic reactions usually have the enthalpy, the heat change, denoted as a negative sign. So, ukiona pahali umepewa the enthalpy, the heat change, and it's negative, it simply means that this is an exothermic reaction. Heat energy is being evolved. Sawa? If it's positive, then that means that the reaction is endothermic. This is a reaction that absorbs heat energy. So our answer is the products have a lower energy than the reactants. Part B. State and explain the observation made when the pressure in the syringe is increased. Okay. Now, I want to draw your attention to the colors. Yes, the colors of the two gases. So when it comes to nitrogen 4 oxide, this is a reddish brown gas. But dinitrogen tetraoxide is pale yellow in color. Now, when we talked about the dynamic equilibrium, we say that when substances are at equilibrium, the rate of the forward reaction is going to be equal to the rate of the backward reaction. So they occur at the same speed. This is to be at constant temperature and pressure. But if you want to change the conditions, okay, let's say maybe you increase the temperature or decrease the temperature, you are going to affect the equilibrium. In such cases, you're going to have one reaction being favored over another. Maybe by decreasing the temperature, you will favor the forward reaction or you will favor the backward reaction as such. Now, this is not fixed. It depends on the particular reaction. So if you decrease conditions such as temperature and pressure, you will affect the equilibrium. It's going to end up favoring one of the reactions over the other. So let's look at our question. In our question, we are increasing the pressure. So how will this affect the equilibrium? Now, if you increase the pressure, the system will always favor the side that has fewer molecules. Let me repeat that. If you increase the pressure, the system will always favor the side that has fewer molecules. Now, what do we mean by the term system? This simply refers to the reactants, the products, and their surroundings. So if you increase the pressure, it's always going to favor the side that has fewer molecules. Now, in this case of ours, on this side of the equation, we have 2 moles of nitrogen 4 oxide. On the other side, we have just 1 mole of dinitrogen tetraoxide. So that means that this is the side that has fewer molecules. So if you increase the pressure, it's going to favor the forward reaction, leading to the production of more of dinitrogen tetraoxide. And what color did we say this was? Pale yellow. So if we have more of dinitrogen tetraoxide being produced, that means that the yellow color is going to intensify. So there is our observation and its explanation. Question number 5. Ammonia gas can be prepared using ammonium sulfate and sodium hydroxide. Part A. Write an equation for the reaction. So ammonium sulfate reacts with sodium hydroxide, leading to the formation of ammonia, sodium sulfate, and water. Part B. Draw a well-labeled diagram of a setup of the apparatus that can be used to prepare and collect a sample of dry ammonia. So there we have our setup. Now, just a few things I would like to note. Number 1, calcium oxide, which is also known as quicklime, is used as a drying agent. Now, the reason why this is preferable is because ammonia reacts with other common drying agents, such as sulfuric acid, and therefore they cannot be used. Ammonium is collected by upward delivery. The reason is because it is less dense than air. By the way, guys, if you find the names, upward delivery, downward delivery confusing for you, just look at the positioning of the delivery tube. In this case, it's pointing upwards, so that is upward delivery. So ammonia is collected as such because it's less dense than air. It's lighter than air. Now, ammonia cannot be collected over water, never, because it is very soluble in water. So what will happen is that instead of you ending up with ammonia gas, you will simply end up with a solution of ammonium hydroxide. So unless this is what you want, don't do it. Moving on to question number 6. Some properties of 4 metals and their oxides are shown in table 1. Okay, let's look at table 1. We have 4 metals labeled A, B, C, and D, their reactions with water and the color of their oxides. Okay, so metal A reacts slowly with steam, metal B reacts rapidly with steam, C reacts rapidly with cold water, and D does not react with either steam or cold water. Part A. Arrange the metals in order of their reactivity, starting with the most reactive. Okay. Now, when we talk about metals, there are 3 broad categories in terms of reactivity with water. There are those that are very reactive and they will react with cold water. Cold water is simply water at room temperature. We are talking about metals such as potassium, sodium, and calcium. In fact, I personally think that C is calcium, okay? Now, and then there are those metals that are moderately reactive. These will not react with cold water, but they will react with steam. So, what is steam? Steam is simply water vapor. If you take water, heat it, to its boiling point and above, you get steam. So, there are some metals that will not react with cold water, but will react with steam. Examples are magnesium and iron. So if you look at the metals that we have 2 metals that react with steam, but B is more reactive. As you can see, it reacts rapidly with steam. A does react with steam, but slowly. Now, if you look at B forms a brown oxide. So this is most probably iron, right? Iron. Now, let's talk about D. D is the least reactive because it does not react with water in any form whatsoever. So if you were to arrange these metals according to their reactivity, the most reactive will definitely be C, followed by B, A, and D being the least reactive. Part B. State the observation that will be made when metal B is heated with oxide of D. Okay, so let's look at D. Its oxide is black. This could be copper. Yeah, because copper 2 oxide is black in color and copper does not react with water, whether steam or cold water. So in this case, we have metal B, okay, so reheated with an oxide of D. Now just look at these 2 metals. B is more reactive than D, as we just discussed. So if we have metal B being more reactive with D, what do you think will happen if you take metal B and place it with an oxide of D, B being more reactive will displace D, okay? So it will combine with oxygen to form the oxide of B. Now D is just going to be deposited as a metal. Now as we stated, D is likely copper, okay? So B twende now to say let's imagine this is iron, because from the information that we have, it looks to be iron. So if you have iron, being reacted with copper to oxide, iron being more reactive will displace copper, combine with oxygen, form iron to oxide. And then copper is just going to be deposited as a metal. So what is our observation? Initially, we had the black solid. This black solid is the copper to oxide, right? But after being reduced to copper metal, we are going to observe a color change because copper metal is brown in color. So our observation is going to be black solid changes to brown, right? Because the copper to oxide was reduced to copper metal. Why was it reduced? Because metal B is more reactive. Okay, Roman 2, oxide of C. Okay, metal B and oxide of C. So C, by the way, was the most reactive of all. So C is more reactive than B. Are we expecting to have any reaction here? No. B cannot displace C because it's less reactive than C. The only way that a metal can displace another is if it's more reactive. So B and an oxide of C, nothing will happen because B is less reactive than C. So it cannot displace C. So what will happen is that the white solid remains. What is the white solid? This is the oxide of C. So it's going to remain the way it is. No reduction will take place. Moving on to the next question. In an experiment to determine the water of crystallization in sodium carbonate, there we have our formula. So that is hydrated sodium carbonate. The X represents the number of moles of water that are present. The data in table 2 was obtained. So let's look at table 2. We have the mass of the crucible there, that is 57.2 grams. Now, when the salt was added onto the crucible, the mass increased to 78.6, okay? It increased because of the salt that was added. Now, when this was heated, what happened is that water of crystallization was lost. The water evaporated because of heating. So as a result, we are going to have a decrease in the mass. The decrease in mass was the water of crystallization that was lost as a result of heating. Calculate part A, the mass of dry salt after heating. Okay, so for us to find the mass of the dry salt after heating, we are going to take the mass after heating, which is 67. But remember, this is the mass of the salt after heating plus the mass of the crucible. Now we are only interested in the mass of the dry salt. So for us to get this, we are going to subtract the mass of the crucible, which is 57.2. That will give us the mass of the salt, the dry salt, as 9.8 grams. Part B, the mass of the water. Now, the mass of the water lost during heating, right? So that means we are going to take the masses before and after heating. We're going to find the difference between these two, and this difference in mass will be that of the water lost during heating. So 78.6 minus 67. This will give us 11.6 grams as the mass of water of crystallization. On to our next question. A polymer was formed using compound M, which has the following structure. Okay, so we have a polymer that was formed using compound M. So that means M is our monomer. So monomers are simply small units which, when joined together, form this long, complex compound that is known as a polymer. Now, name compound M. M is phenylethane. Part B. Draw a section of the polymer showing 3 repeating units. Okay, so this is our monomer. So number one, what you're going to do is we are going to split apart the double bonds. The polymer is not supposed to have a double bond in this case. So we're going to split apart this, ensuring that we only have single bonds throughout. So once we have done that, we are going to place 3 of these, just repeating them the way they are. And we end up having a section of the polymer as such. Part C. Give one advantage of using this polymer over natural polymer. Okay. Now, when it comes to this polymer, phenylethene, it has a variety of uses. It is used in production of plastics, such as in utensils, cups and plates. It's also used in the manufacture of toys and even car parts. So, phenylethene is preferable to natural polymers such as wood. And yes, wood is actually a polymer. So when you talk about a polymer, this is simply a complex molecule consisting of many simpler molecules just joined together. Wood contains cellulose. It also contains lignin. And for those of you who do biology, just use your knowledge. What is cellulose? What is lignin? These are simply complex carbohydrates. And complex carbohydrates contain many units of simple carbohydrates such as glucose joined together. So wood is a natural polymer. You have wood, you have cotton, you have wool, yes, the wool from the sheep. All of these are natural polymers. But the question is asking us, why is it preferable to use phenylethene, which is a synthetic polymer, over natural polymers such as wood? Now, the reason is because actually there are several reasons. Number one is it's cheaper, right? Number two is that it's also more durable. It lasts longer. Natural polymers usually degrade over time. They break down over time, especially when they are exposed to moisture or even pests or certain environmental factors such as humidity. They break down over time. Number three is that phenylethene can also be molded easily to form different shapes. And that is why it can be used for a variety of purposes, such as even making, disposable cups, toys, and even parts of cars, because it can be molded to different shapes quite easily. Okay, not quite easily, that easily, the way I'm making it sound, but easier than natural polymers. Okay, question number 9. Figure 1 shows a setup that was used to investigate the product of a burning candle. State and explain the observations made in the YouTube. Okay, before I do that, let me explain the setup. So we have a candle. A candle is a hydrocarbon. A hydrocarbon is a compound that contains carbon and hydrogen only. Now, when hydrocarbons burn, they form 2 products. Carbon dioxide and water vapor. So in this case, these 2 products are going to pass into the YouTube that contains anhydrous cobalt-2 chloride. Carbon dioxide has no effect on anhydrous cobalt-2 chloride, so it's simply going to pass into the next flask. What about water vapor? Yep, this is going to bring about a certain observation. Now, anhydrous cobalt-2 chloride is actually blue in color, but when it's hydrated, when it absorbs moisture, it changes to pink. So in this case, when it comes into contact with the water vapor, it's going to change to pink. So that is our observation. Now, what is our explanation here? Candle on burning produces water and carbon dioxide. Water will combine with the blue anhydrous cobalt-2 chloride to form pink hydrated cobalt-2 chloride. Now, Roman number 2. How the pH of distilled water changes with time. So carbon dioxide will pass into this flask containing distilled water. Now, carbon dioxide is slightly soluble in water. So some of it is going to dissolve in water to form weak carbonic acid, okay? Now, initially the pH of the distilled water was 7. It's neutral. But when carbon dioxide dissolves in water to form carbonic acid, it's going to decrease slightly from 7 to 6. So it's not going to go lower than that because, as stated, the acid that is formed is weak carbonic acid. It's a weak acid. So it's going to decrease from 7 to 6 as a result of the formation of this acid. Part B, state the role of the pump. So the pump has the role of creating a suction force that sucks the gaseous product into the apparatus. Question number 10. In an experiment to determine the molar heat of neutralization, 100 cubic centimeters of 1 molar sodium hydroxide was added to 100 cubic centimeters of 1 molar hydrochloric acid. The data obtained is shown in table 3 below. Okay, so we have table 3 over there. So we have the initial temperature and the maximum temperature. Okay, let me explain how this happened. So let's imagine you took, the hydrochloric acid, placed it in a beaker, and you took a thermometer stud. Now, that temperature that you got is the initial temperature, which was 20.4 degrees Celsius. On addition of sodium hydroxide, these two are going to react with one another. An acid reacts with a base to form a salt and water. So sodium hydroxide will react with hydrochloric acid to form sodium chloride plus water. So this is a neutralization reaction. And neutralization reactions are exothermic. They give off heat energy. As we can clearly see, the temperature rose from 20.4 to 26.5. What does this tell us? It tells us that heat energy was released into the surrounding, and this is the reason why we have an increase in temperature. Sawa? Now part A, calculate the heat change. So how do we calculate the heat change? We use the following formula. Mass multiplied by the specific heat capacity multiplied by the change in temperature. What is our mass? We don't have the mass at this point. We only have the volume. So we know that the volume of sodium hydroxide was 100 cubic centimeters and that of hydrochloric acid was also 100. So the total volume was 200 cubic centimeters. But bear in mind, this is the volume. We want the mass. So for us to get the mass, we are simply going to take the volume multiplied by the density, which we have been provided with. So 200 multiplied by 1 gives us a mass of 200 grams. Okay, now that we are done with that part, the second specific heat capacity, which we also have, 4.2. And lastly, the change in temperature. So for us to get the change in temperature, we are simply going to find a difference, the difference between the maximum temperature and the initial temperature. And that gives us 6.1. Multiply everything, and our answer is going to be 5,124 joules. Now, let's pause there. What we're going to do is we are going to divide this by 1,000 to get it to kilojoules. It's quite a large number. So we're going to divide by 1,000 to get 5.124 kilojoules. We should to Apple, we are going to place a negative sign. Apple to take a negative sign. Why? This negative sign shows us that this reaction is exothermic. Heat energy was given. So exothermic reactions, enthalpy changes of exothermic reactions are assigned a negative sign. So our final answer is negative 5.124 kilojoules. Tunamalizana hapo with part A. Part A, Roman 1. Roman 2. The molar heat of neutralization of hydrochloric acid. Now, what did we just calculate? Okay, what we calculated was the amount of heat energy that was given off when 100 cubic centimeters of 1 molar hydrochloric acid was used. What is this part of the question after? It wants to know the amount of heat energy that will be released if 1 mole of hydrochloric acid will be used. Okay? So first things first, we need to find the number of moles in what was carried out in the experiment. In the volume of hydrochloric acid used. How do we do that? We use this formula. Moles are given by volume multiplied by the molarity over 1000. Our volume is 100, our molarity is 1 over 1000, and we get the number of moles as 0.1. So these are the number of moles of hydrochloric acid that were used in this experiment. Question yataka nini? What about for 1 mole? So if 0.1 mole of hydrochloric acid evolved 5.124 kilojoules of heat energy, what if we used 1 mole? How much heat energy are we going to liberate? Are we going to evolve? So at this point, it's simply a matter of cross multiplying. So if this produces that, what about 1 mole? And our final answer is going to be negative 51.24 kilojoules per mole. So these are the kilojoules of heat energy that will be released when 1 mole of hydrochloric acid is used. Na msisahau negative sign, okay? Exothermic reactions. Part B. The molar heat of neutralization obtained in 10A Roman 2 differs from that obtained using aqueous ammonia and hydrochloric acid. Explain. Okay. So essentially we have 2 sets of experiments. The first one is what was done, hydrochloric acid being reacted with sodium hydroxide. The second one is a reaction between hydrochloric acid and aqueous ammonia. Aqueous ammonia is simply ammonium hydroxide. Now you will note that in both cases, hydrochloric acid is constant. Okay, it's present in both reactions. The variable is the type of alkali used. You know, the type of base used. In the first instance, we used sodium hydroxide. This is a strong base. In the second instance, ammonium hydroxide was used, which is a weak base. So the question is telling us that the amount of heat energy released is, different if you were to carry out these 2 reactions, which makes sense because are you expecting that the same amount of heat energy to be released when using a strong base and a weak base? Of course not. So let me explain the reason why. In the case of sodium hydroxide, this is a strong base. What is a strong base? This is one that completely dissociates in water. It breaks down in water, leading to the formation of ions. You're going to have sodium ions and hydroxide ions. So it's these ions that will then react. So all strong bases completely dissociate in water to form ions. So you end up having a high concentration of ions. Now, in the case of aqueous ammonia, ammonium hydroxide, this is a weak base, and weak bases do not fully dissociate. So what happens is that some of their molecules will break down to form ions, others will not. So they're just going to remain the way they are. So at the end, you are going to have less ions present compared to sodium hydroxide. Now, when the reaction occurs and heat energy is produced, some of the heat energy is going to be used to break down the molecules that did not dissociate. Let me repeat. When the reaction occurs between the ions that are present and, the ions from hydrochloric acid, it's going to evolve heat. Yeah, it's going to produce heat. Some of this heat energy is going to be released into the surrounding, but some of it is going to be used to break down the molecules that did not dissociate. So overall, less heat energy is given off to the surrounding. Question number 11. Iron is extracted from its ore in a blast furnace. The raw materials used are iron ore, coke, air, and limestone. State the role of each of the following in the extraction process. Okay, so Roman number 1, we have limestone. Limestone is simply calcium carbonate. So when this is heated, it's going to decompose. It breaks down, leading to the formation of calcium oxide and carbon 4 oxide. Each of these two has their purpose. They have a role that they play during the extraction process. So calcium oxide, for example, helps to remove impurities in the ore. Carbon 4 oxide, on the other hand, is reduced by carbon to carbon 2 oxide, which then reduces the ore. So it's going to be reduced to carbon 2 oxide, and carbon 2 oxide is the main reducing agent. Now at this point, I'm not going to go into details explaining how iron is extracted from its ores, because this will take up the whole lesson. Now, this is also something that I have already discussed in depth in another video. By the way, this is a topic you are going to learn in Form 4. It's under metals. So you're going to learn about extractions of different metals such as sodium, aluminium, copper, zinc, iron. All of these I have discussed. So there's a playlist titled Metals. You are going to find all of these. I've even discussed past KCSE questions on such. So if you're free, check them out. Now, let's proceed to Roman 2, coke. Coke is simply carbon. So the carbon is burned to produce carbon 4 oxide, which is then reduced to carbon 2 oxide and is used as the main reducing agent. Part B. State and explain why the iron obtained is not suitable for making bridges. Now the reason is because the iron obtained is brittle, okay? It's weak and it's not as strong as it should be. The reason why it's not as strong and the reason why it's brittle is because it tends to contain impurities such as carbon. So because of this, it cannot be used to make bridges. Can you imagine how lethal this will be, using brittle iron to make bridges? Hey. Okay, now question number 12. Table 4 shows some properties of 3 substances. Complete the table by filling in the type of forces in each substance. Okay, so we have X, Y, and Z, their melting points, and electrical conductivity in the solid state and the molten state. Now, this is where I usually focus on first, okay? Because the information that is given based on the electrical conductivity can be enough for you to answer the question. Okay, let's look at X. In the case of X, this is a poor conductor in the solid and molten state. So this is probably, okay, it is actually a molecular substance. So the type of forces that are going to be present are van der Waals forces. The structure is a simple molecular structure. Why am I saying it's a simple molecular structure? Look at the low melting and boiling points. Why? So Y is a good conductor in both solid and molten state. This is a metal. So which type of force is present in metals? We have electrostatic force or the metallic bond. Now what is an electrostatic force? Electrostatic forces of attraction are those forces of attraction that are present between oppositely charged particles. Okay? So in the case of metals, you are going to have the nuclei being positively charged due to the presence of protons, right? So nuclei are positively charged because they have protons. Protons are positively charged, right? So nuclei overall are positively charged. These are going to be surrounded by a sea of delocalized electrons. Okay, a lot of delocalized electrons. Now, what are delocalized electrons? These are simply the valence electrons. Valence electrons are electrons that are found in the outermost energy level. Now, in the case of metals, their valence electrons are capable of moving within the structure. And that is the reason why they are referred to as delocalized. Okay, yani haziko pale pamoja, they are delocalized, they move within the structure. So you're going to have this force of attraction between the negatively charged delocalized electrons and the positive nuclei. So in short, a force of attraction between oppositely charged particles. And that is what is referred to as the electrostatic force of attraction. Which type of structure is present? A giant metallic structure. Moving on to Z. Z is a poor conductor in the solid state, but it's a good conductor in the molten state. This is an ionic compound. Ionic compounds do not conduct electricity during, when they are in solid state, because the ions are held in fixed positions, so they cannot move around. But when they are dissolved in water or when they have been melted, what happens is that the ions now become free. So they become mobile and they are capable of moving within the structure, conducting the electric current. So which type of force is found between, in ionic compound? Again, electrostatic force of attraction. Why? Because when you talk about ionic compounds, this is whereby you're going to have a force of attraction between ions. One of these ions is going to be positively charged, the other is going to be negatively charged. So essentially, a force of attraction between oppositely charged particle. Electrostatic force. What about the structure? It's a giant ionic structure.